So let's take a look at just a couple of other types of nuclear reactions beyond the classic alpha, beta, and gamma decay. One of them is called positron emission. A positron is a positively charged electron. That sort of doesn't make any sense, but these things actually exist. It has the same mass as an electron, but it has a positive charge instead of a negative charge. The symbol we can still use in E, atomic number of +1 instead of -1. And it's still a mass number of 0 because it doesn't contain any protons or neutrons. So positron emission is treated just like any other decay. You produce the positron and another either stable or unstable nucleus, another nuclide comes out. The overall effect of positron emission is that your atomic number will go down by 1 on the right side of the equation, but the mass number will stay the same. So polonium with an atomic number of 84 and a mass number of 207, if it produces a positron, will become bismuth with atomic number 83, but still a mass number of 207. Now, if you're sort of following the mass or the math that's going on here, if the number of protons goes down by 1 as this positron is being produced, but the total number of particles in the nucleus stays the same, then something must happen as the positron is released that causes a proton to turn into a neutron. This is one of the many strange things that nuclei do in atoms. Similar is something called K-capture. K-capture is essentially the exact reverse of beta emission. Beta emission or beta decay is when an atom releases this electron, or releases it, and becomes a little bit more stable. In K-capture, the nucleus actually captures or absorbs an electron from the first shell, which is sometimes called the K shell. Since it's absorbing an electron, the electron is going to end up being on the left side of the equation. And since the atomic number, if you will, of an electron is -1, then that means that, again, the overall effect of absorbing an electron is that the number of protons goes down by 1, but the mass number doesn't change. So anytime the number of protons goes down by 1, but the mass number doesn't change, we have essentially a proton turning into a neutron. And that's essentially what happens. An electron from the K shell is absorbed, it combines with a proton, the charges cancel, so you get a neutral compound, a neutral particle, and the mass number is conserved, so you have a neutral particle with a mass number of 1. Well, that's a neutron. And so the number of neutrons increases by 1, but the overall number of particles in the nucleus stays exactly the same. So K-capture is the reverse of beta decay. This is a diagram that shows the stable and unstable isotopes as you increase the number of neutrons and the number of protons. Neutrons is usually represented by the letter N, and the number of protons represented by the letter Z. When the number of neutrons and protons are the same, N to Z ratio is 1 to 1, you get that straight line with a slope of 1. And you'll notice that for the lighter elements, number of protons are below about 30 or so. They kind of follow that straight line, but once you get to about element zinc or above, then the isotopes start to have more neutrons in them than protons, and they become unstable. If you look, the group of little dots ends right a little bit above 80, as a matter of fact, right at 83. There are no stable isotopes above atomic number 83. Bismuth is the last stable isotope. The rest are all radioactive. So you'll see there's a lot of radioactive isotopes, but there's these black dots all the way along that shows that there are stable isotopes. The little arrows from alpha emission, beta emission, and positron emission show the general direction that you will head in on this graph if you if you undergo one of those things. So alpha emission decreases both the number of neutrons and protons because you're releasing protons and neutrons in the form of alpha particles. Beta emission actually decreases the number of neutrons, but it increases the number of protons just a little bit. And positron emission is exactly the opposite. Let's talk a little bit about half-life. So there's something we're going to discuss later on in the year, second semester, called kinetics, which is essentially just a study of reaction rates, how fast reactions go. nuclear decay reactions follow something called first-order kinetics. And what that means, without getting too into it right now, is that the more starting atoms you have, the faster they will decay. But what that means is that if you increase the number of unstable isotope atoms at the beginning and they decay at a faster rate, it means that the amount of time it takes for that decay to happen basically doesn't change. It's constant, because the more you have, the faster it goes. And so the amount of time it takes for those to all decay is about the same, regardless of how much you have. It sounds weird and counterintuitive. It sounds like it shouldn't make sense. But take a look at it in the context of something called half-life. Half-life is the amount of time it takes for half of your unstable atoms to decay. So after one half-life, you'll have half the number of unstable atoms that you started with. After a second half-life, you'll still have half the number of what you just had, so about a quarter of what you originally had. If you start with 1,000 atoms, after one half-life, you will have 500. After a second half-life, the same amount of time, you'll have 250. After a third half-life, you'll have 125, and so on. So if you think about it, as the half-life occurs, fewer and fewer of these atoms are decaying as there get to be fewer and fewer of them. So the more you have, the faster the decay will happen. That means that it'll take about the same amount of time to get halfway done. If you have 1,000 and let's say the half-life of this isotope that you have is 5 years. You have 1,000 atoms. After 5 years, you'll have 500 left. If you start with 2,000 atoms, you've doubled the amount. Well, the decay is going to speed up. The more you have, the faster it goes. And it's going to speed up so that after 5 years, you have 1,000 atoms left, half of them left. Well, in the first example, when you started with 1,000, it took you 5 years to get down, to lose 500 of those atoms, to get down to 500. When you doubled the amount, it took you 5 years to lose 1,000 atoms, to decay 1,000 atoms. So it went faster, but the amount of time it takes is the same. That's what first-order kinetics means. We'll go into this in much greater detail later on. But what it means is that we have a relationship then between the amount of stuff we start with and the amount of time it takes and how long the half-life is. And we can represent that by this little equation here. A is the amount of substance, the amount of unstable isotope that's left after a certain amount of time. A with a little 0, which we call A naught, is the amount of atoms that you started with, your starting material. The half in parentheses, well, we're talking about half-life. Half of it is going away. The exponent T over H, T stands for the amount of time that you're allowing this to decay, and H is the half-life itself. So we can rearrange that a little bit. I don't like having a fraction raised to an exponent, but if we just rearrange it a little bit, we get a slightly more workable version of this. So A is equal to A naught times 2 to the negative T over H. If you understand your exponent rules, you'll know why that looks that way. Okay? So all we need, really, we have 4 variables, A naught, T, and H. We need just to know 3 of them, and we can solve for the 4th one. So let's do an example. So you discover a new radioactive isotope. That isotope has a half-life of 1.23 years. You start with a sample that has a mass of 45 grams. That's A naught. How much of that isotope will be left after 6.7 years? 6.7 years is the amount of time. That's T. The half-life is 1.23 years. That's H. The amount you started with was 45 grams. That's A naught. You're solving for A. So if you plug in the numbers, you have A is equal to 45 times 2 raised to the negative 6.7 divided by 1.23 power. Plug it into your calculator, you get a value of A that is 1.03 grams. So if the half-life is 1.23 years, and you let this decay for 6.7 years, you're going to have a gram, a little more than a gram of your original unstable isotope left. You started with 45, you're down to 1 gram. Well, that's several half-lives, though. 6.7 years is several times 1.23. And so each time you go 1.23 years, you lose half of your atoms. So that's how you calculate it. Now, the calculations can get a little bit more interesting, like if you're trying to solve for time or half-life, T or H, because of where they are in the expression, they're in the exponent. You then have to use a little bit of natural logs. It's a logarithmic relationship, and we can talk a little bit about that now, but it'll make a lot more sense when we do first order, second order kinetics in the second half of the year. So give it a shot on the worksheet, and make sure that you take good notes on the video.